All right, so picking back up here, we're going to do number 2 again, just to remind everyone who hasn't come to a few of the problems, give you some help to do on first day back. If they're really kind to you, go ahead and give you your homework, plenty of time left in class. Merry Christmas, no homework. So,
Can you get our test back?
test back? Yeah. 60 kilogram lady walks out a 35 kilogram board, 3.2 meter long, and it's uniform, meaning evenly distributed in the mass. Bolts holding the diving board to the foundation are 0.52 meters from the front edge. How much force must the bolts withstand to keep the board from jumping over? Okay, so that was the problem. I know we've already worked before to go back to it again. Step 1 is always draw a picture and label everything that's going on. So I got a diving board here, and I'll draw kind of my diving board base, right? And then the diving board comes out like that, right? And I got a 60 kilogram lady on the end. Right, on the end of my diving board. I got 2 bolts over here at the back. Over here at the back. Now, let's label all of our forces. Actually, I skipped a step. We need to pick a spot that's going to rotate around. Okay, where is this board going to rotate? Where's the rotation point? Sorry, it's not the middle here.
Front edge.
It's going to be the front edge of the base. I mean, think about this. Where's the board going to want to rotate around? It's going to want to rotate right there. Does that make sense to everyone? It's going to want to tip right there at the front edge. Sometimes it's the middle, but whenever something's offset, the point it wants to rotate around is wherever the thing's supporting it is, right? Wherever the thing's supporting it is. Just because the fulcrum on a seesaw, right, the thing that's normally at the middle, just because the fulcrum of the seesaw isn't at the middle sometime, here, shift the fulcrum over to one side, that way one side longer, one side shorter, doesn't mean the seesaw's still going to rotate around the middle, right? The seesaw's still going to go around the fulcrum, right? And it's not in the middle anymore, okay? So there's the spot it's going to rotate around. Now I need to figure out forces that are causing rotations. All right, so where are my torques? Where are the forces causing rotations? The woman, right? She's got a force going down. What's that force? Good, force of gravity.
And then the bolts.
All right, so I got the bolts. Which way are they going?
Up.
Which way are the bolts trying to? They're pulling it back down, right? The bolts are trying to keep the board. Which way does this board want to go with the woman? Well, it wants to spin up, right? The woman wants to go down, meaning the bolts want to go up. So to prevent the bolts from going up, the bolts hold the board down. So F, and I'll label it FB for force of bolts. Okay? Got one other force. Center of mass. The board has mass, right? And we can assume all of that mass is located here at the center of mass. So this becomes the force of gravity of the, let's label it CM for center of mass. In other words, the board has weight. The board has weight. And even if there's no one on it, right? Even if there's no one on it, if you offset your fulcrum off to the side, the thing wants to rotate, right? I mean, right here, the meter stick wants to rotate down like that, right? Because of the center of mass around the 50 centimeter mark. And it wants to fall back down. So there is a torque naturally just because of the board itself. All right, let's choose positives and negatives. That way, which one do you want to be?
Positive.
Positive. That must mean everything that goes that way is negative. Sum of the torques must equal 0. So let's come back up and let's see what torques I have. The torque caused by the lady, right? Tau lady. Is it positive or negative? Positive, right? We said the best way to get that, put your hand on the lady and follow the force. Which way is it trying to make it rotate? Down and around here. That's the positive direction. Okay. So that's going to be positive. Plus, center mass, positive or negative? Positive also, right? Going the same way as the lady, down and around this way. So, torque, center mass, plus, force of the board, positive or negative? Negative, right? It's going down too, but it's not about down versus up. It's about which way does it make it want to rotate. Take your finger here, right? When you go down, there's the rotation point over here. So you go down and around the other way. Opposite is how it makes it want to rotate. Does everyone see that? Yeah? All right, so I'm going to have a negative torque of volts, and all those guys add up to be 0. Another way to think about this is the volts torque has to balance out the ladies and the center of mass. Okay? They have to balance each other out. All right, so the equation for torque is what? What's torque equal to? Force times distance. Good. So this becomes Fg of the lady times the distance that she is. This becomes the force of gravity of the center of mass times its distance, right? Minus, this is the force of the volts times its distance equals 0. Now we start plugging things in and breaking it all down, right? Distances. Let's pause and let's go back up to our picture and let's try to figure out these distances. We're told the entire board is 3.2 meters long. Okay. The bolts holding the diving board to the foundation are 0.52 meters from the front edge. So the bolts holding the diving board to the foundation are right here. This would be 0.52 meters from the front edge of that foundation, right? Okay. How much force must the bolts withstand to keep the board from tipping over? I'm still distances here, right? I need the distance. By the way, what distances do we use relative to? I guess that's what I'm looking for here. Do we use it relative to the center of the board? No, to the fulcrum. So I got to get all the distances measured to the fulcrum. That means I need, for the distance of the lady, I need that. How do I get that?
3.2 miles.
Yeah, 3.2 minus 0.52. What does that come out to be? 0.68. Everybody see how we got that? Okay. How am I going to get that distance to the center of mass? How am I going to get that distance? Okay, that would work, right? We know this length right here, right? We can figure out that length right there. It's to the center of mass. So that's the very center of this uniform board. 3.2 divided by 2 is what? 1.6. So if this is 1.6, 1.6 minus 5.2 will give me that distance. What is it? We okay in getting those distances? Just gotta kind of think about it.
Yep.
Alrighty? Now let's use those distances and start plugging them back into our equation down here. Force of gravity of the lady is her mass times gravity, and her mass was 60 kilograms. Gravity, 9.8. How far away from the board, how far away from the fulcrum was she? 2.68. Plus, force of gravity of the center of mass will be the mass of the board, which was 32, am I correct? Yes.
No.
No. 35. 35 kilograms, that's its mass times gravity. 9.8 times distance from the center of mass to the fulcrum is what? 1.08. Minus, I'm looking for the force of the bolts. Now, how far did the bolts have to the bolt? 0.52. Okay, now it's just simple algebra, right? So what's the answer here? Say that again, Brooke. With sig figs, 2 sig figs there, from 3,700 newtons. Okay. A lot of force. A lot of force. Shorter distance, right? We talk vaguely about mechanical advantage. Okay. The longer the lever that you have to push with, I mean, the diving board, this is a pretty long lever out there. Force times distance, having that extra distance basically multiplies the force. Gives you a greater torque. The farther distance you are away, the more torque you have. That's why crowbars, it's so much easier to lift something with a crowbar than it is just to lift it straight up, right? I mean, has anyone ever actually tried to lift a tire? Sure. You know, I assume you've done that. How about one of those manholes? You know what I'm talking about? Little metal top on the hole in the street, right? A manhole. Has anyone tried to lift the metal top? How heavy is it? I mean, could you just lift it all by yourself? I mean, not really. Most of them, no. You're not just going to reach down and yank it out too much. You got to have a crowbar, right, to stick in there and use that torque, right, to be able to press down on it. It gives you a large lever that you're pushing down to be able to lift that guy up. Okay, so the more distance you have, it basically multiplies your force. Right? Multiplies your force. Any questions about this? We feeling okay still with torque? Yeah? I don't think I got anything on the next page. Nope. So I'm going to let you work a few problems.